All right, what's going on, everyone? Making this video for a couple reasons. I feel like there's an abundance of sort of lang chain level content out there, pretty high levels of abstraction when it comes to large language models. And, I'm sure there's plenty of content out there that'll go through the nuts and bolts of these language models, but I think there's a lot of value in understanding how they work, particularly if you want to better understand, the decoding parameters that you're using. If something breaks and you need to debug something, it's kind of interesting to know how that works. If you have to build one of these things, this would be a prerequisite. And if you're a researcher and want to extend these things, at a minimum, you're going to have to understand how these things are built before you could even, think about extending some component of this system. So what I'm going to do here is I'm going to walk through the code for the Llama 2 repo. And I couldn't find a video that did this. And, I just wonder if it might be useful to go through, the definition of the model, implement this transformer, and, annotate sort of some of the code that I'm seeing almost line by line. I've been doing this lately as an exercise to almost train my own language model and just, copy someone's code line for line. And I'm not talking about copying and pasting. I'm talking about writing it out, forcing yourself to think about the way that the authors of this code laid out the repository, the decisions that were made syntactically, stylistically, and not only that, it kind of forces you to think, why did they do this? And make sure that you're understanding all of the components that are being used here. And so, that's what I'll be doing. I'm going to be going through, these three Python files, starting with model.py. These are essentially the required files to use Llama 2. And the other thing to say, and I'll get off my soapbox after this, is I think there's so much abstraction in the community right now, which is a fantastic thing for a lot of developers. But when you use something like Hugging Face, for example, you're abstracted from the PyTorch layer. You're not exposed to those low-level details. And I think it's easy to forget that there is a transformer model that someone has to implement. There are a lot of decisions being made, and I feel like getting down to that level sort of demystifies all of this. Not to mention, I think just being really rock solid on PyTorch in the same way that you might be solid on Pandas is a useful skill to have. So yeah, without further ado, that's what we'll be doing. I'm not sure how long this will take. I might have to break this up a little bit, but let's start with model.py. So if you see any mistakes here, it's likely my fault. So I wrote all of this out. So if there are any bugs, it's potentially my fault. So let's start from the top. So you've got your typical imports. There's the use of a data class, and they also type annotate a lot of their content, which is kind of interesting. I find it useful from a readability standpoint, but also I tend to use arg parser a lot and simple namespace objects. So this was nice to see sort of another approach for giving yourself some sort of a configuration object. They're using fair scale in this module. This is a way of implementing model parallelism. So these large language models are massive. Most of them don't fit on commonly available GPUs. I think once you hit something like 2 or 3 billion parameters, you can no longer train on a single GPU. I think you can still get away with loading a 7 billion parameter on most commonly available GPUs. In fact, you can. But I think once you go beyond that, you need to start thinking about how you're going to parallelize this model across multiple GPUs to be able to even perform inference. So it's worth digging into the details around model parallelism. That's one approach. When you're training, you've got data parallelism, you've got pipeline parallelism. So there's a variety of approaches here. So we're going to talk a little bit about what these different approaches to parallelization are doing. Just as a note, I think I had to import. I had to make one modification to this. So if you look at the init file, and originally, I think when I pulled down the code, parallel embedding was not here. And so if you're seeing that you cannot import parallel embedding, just go ahead and toss it in there. One of my favorite features of VS Code is being able to click into the source code, right? So I can actually like trace back to the original implementation of layers. And here I am looking at the code that that was written by the PyTorch authors. And I guess just one other thing to say is I really like this repository because this is, essentially world-class PyTorch code written by engineers at Facebook. Facebook, they've written PyTorch, they've, developed this Llama model, and I feel like it's like a great opportunity to, see how they use PyTorch, essentially use this as a really nice canonical reference example for how to write good PyTorch code. And not only that, use some experimental portions of the code base. So you can see, we're using fair scale in this case, which is sort of experimental research code that eventually gets upstreamed into PyTorch if the community finds it useful. So I just wanted to point out that you can click through and you can actually inspect the code, and I think there's a lot of value in this particular repo because it should be sort of a really solid reference for people who are learning PyTorch and wanting to dig into the details of language modeling. So then we get into the model arguments, and let's talk a little bit about the architecture here. So I pulled in a couple of the parameters that you would get when you actually download the weights. I'm not going to cover sort of how you get the weights. I trust everybody can figure out how to agree to that agreement, download those weights, and with that there's going to be a params.json file that gives you these details. And so just as a quick overview, the dimension here is going to be the embedding size. This is going to be the representation size of your tokens as it passes through the model. The number of layers is 32 in the base case. This is the 7 billion parameter configuration. The number of attention heads, so again, we're probably all familiar with the transformer architecture to some extent, but what you're doing is you're taking that 4096 dimensional vector, you're slicing it up into 32 chunks, and the attention mechanism is going to attend to those individual chunks. So we can get into the details a little bit more. The number of KV heads. So this is really one of the interesting aspects of this, and I'm actually going to pull up a little more detail about the grouped query attention. I think they call it GQA. And so you see there's a distinction between the number of heads and the number of KV heads. So N heads corresponds to the number of query heads that are going to be in the model, and the number of KV heads is potentially going to be smaller than that. So if you look in the case of the 70 billion parameter model, you've got 64 heads, and then you've got 8 KV heads. So you've got an 8-to-1 ratio. So for every 8 query heads, you're going to have 1 KV head. So let's see what that actually looks like pictorially. What I really like about group query attention is that it's sort of an interpolation between two possible extremes. So this is the original transformer architecture where you've got multi-head attention. You've got, imagine this as a single token, right? That's probably the right way to interpret this visual. So each of these queries is going to be one of those sub-tokens. So in the case of 4096 dimensions, you can imagine 32 chunks, each of which are a query. Similarly, when you attend to the keys, when you take a dot product attention with the keys, there's going to be a corresponding key for every single query, and then you're going to take a weighted average of the values. But the important point here is there's a one-to-one correspondence between queries and keys. And then on the other extreme, which you'll see with the Falcon series of models, for example, they do multi-query attention where you have again, maybe those 32 attention heads, but they're all querying against a single key. And, so that's a really extreme scenario. And you might say, well, how the heck are we going to take a 4096 dimensional representation of a token, that we need to attend to, and squash it down to some really tiny portion, some 1/32 portion of 4096. And I think maybe that's the realization, is that you're probably going to lose some information there. The upshot of this, why do we do this? The upshot of this is that you have way less information to keep around in memory, in GPU memory. That's one of the biggest bottlenecks of decoding and inference speed is having to retrieve a huge key value cache from GPU memory. And so to the extent that you can reduce the number of, or I should say the size of this key value cache, you can decode more quickly. And so what group query does is it takes those ideas and it interpolates between them. So you've got, say those 32 attention heads here, but maybe you only have, a small fraction of the keys. And so for, essentially what you're going to do is the picture will wind up looking like this. It's just that this term will be repeated twice. In this particular case, it's a 2-to-1 ratio. So, this would query against this and this would query against this, but you should imagine this as being repeated. And so we'll talk about that in the code. And again, the point being here is that you're interpolating between that loss of information when you compress that token too much, against the memory savings of discarding some of those keys. So I think in the 7 billion scenario, they don't use any any downsampling. I think they have the same number of key value heads as the number of heads. So just wanted to point that out there. Okay, moving on, the vocab size, that's that. I think that's just defined based on whatever they made the decision of. Maybe it varies by model size, I just don't know. A multiple of, so they say make the swig-glue hidden layer size a multiple of a large power of 2. I don't really know why they're doing this. It might be a hardware optimization. I've seen things where GPUs are particularly efficient if you can get a batch size that's some power of 2 and so on and so forth. So there might be something there. It also just might be a design decision. The FFN dim multiplier. So in the case of the 70 billion parameter model, this is 1.3, so that's actually going to increase the size. And then I think for the other one, for the 7 billion, for example, I don't think there's any multiplier at all. The norm epsilon, this is for the layer norm, so you don't divide by 0. Max batch size, so 32, okay, this is just, this is giving people a sensible default in order to pre-fill certain caches and tensors. Max sequence length of the model is 2048. I don't think they trained on anything longer. I don't think that's possible with this model. This does beg the question of the discussion of rotary embeddings versus things like alibi. These are all positional and encoding techniques, some of which are able to extend beyond the length of the training set. I frankly need to do a little more digging on some of the strengths and weaknesses, but nevertheless, they did use rope embeddings, rotary embeddings here. And we're going to talk a little bit about that. So there's a couple ways that I can go about going through this code base. I can either sort of go top down, or I can go bottom up. So top down would be to say, okay, let's start with the transformer model itself, and it's interesting the way I wrote this out. Kind of weird, I have my if name equals main block there. But yeah, so one way to go about this would be to say, okay, we know we want to implement a transformer. Let's put the placeholders for the different sublayers. Or we can say, okay, we kind of know where we're going. Let's start with the individual layers and build up from there. And so I think I'm going to go with that approach. I'm not sure if there's a better way to explain this, but yeah, that's the plan for now. And I just want to move this because this is bothering me. Because this typically goes at the bottom of the script. And so this is going to have to go here. Okay. So let's take it from the top then. So again, what does a transformer have? It has an attention block followed by a feed forward block, and those two components make up a transformer block. And so what we'll do is we'll start with an attention mechanism. And again, this is a causal decoder, and so we're going to be attending to all of the words that came previously in the sequence. You can see, I've made a bunch of notes here because I was trying to understand this. I just went through this today and yesterday. So there is a distinction between the number of heads and the number of KV heads. We talked about the group query attention, so you can like just maybe give yourself an example of a 2-to-1 ratio like we saw in that picture. You have 32 query heads, 16 key value heads. This is again reducing decoding time by reducing the number of keys and values stored in the key value cache. Basically if it's specified, if it's not specified, then just go with the same number of heads. So that settles it. For the 7 billion parameter model, we are going to have a 1-to-1 correspondence. Now we're going to initialize model parallel world size. This is basically going to enable you to split this model across multiple GPUs. I haven't really prepared much for this. This is me just kind of riffing, so forgive me if my visuals are crap. So what's going to happen is you're going to have, essentially, an input sequence like the, quick, brown, right, fox, whatever. And so you're going to have the embedding layer, but let's just assume for a moment we're only focused on the attention layer followed by the feed forward layer, right? So this is going to be essentially a transformer block, and this is going to get repeated a bunch of times. And I'm going to give myself a little more space here, and let's just replicate this a couple times. So, this is essentially what the transformer looks like. And, as you're, feeding in data, you're going to be passing through, data up through the transformer layer by layer. There's going to be some number of layers. I think in the 7 billion model, there are 32 of them. And so really what I'd like to point out is what happens in a model parallel scenario. Essentially what you're going to do, and this is probably a bit of a gross oversimplification, we can try to unpack the details a little, but suppose you had 2 GPUs. What we're essentially going to do when we do model parallels, we're going to take this slice, this kind of like vertical slice. I always forget if people call it vertical or horizontal parallelism, but nevertheless, like this is sort of the way in which we're dividing up the model. By and large, the operations when you split in this manner are independent. For the most part, there's some details to work out there, but a lot of the operations can be split in this model parallel fashion, and so that's what's happening with model parallelism. So the number of local heads. So this speaks to this idea. So we're going to split up the attention mechanism. So we're going to take 32 query heads. So let's take an example. Let's take 32 query heads and 8 GPUs. Each GPU is going to get 4 query heads. Each GPU is going to own 4 query heads, and that's going to be the case for every part of the sequence. So in my example of the quick brown fox, whatever, each position in that sequence owns the 4 query heads. So I don't know if that's like a particularly interesting point, but so GPU 0 is going to handle the first 4 query heads and the 2 corresponding key value heads. And again, this sort of matters when it comes to how you implement the attention mechanism. But you can see there's like this natural ability to parallelize some of these operations across GPUs. And so that's why we're talking about the number of local heads. So a particular GPU is going to own a certain number of local heads. And a very natural way to do this is to say, okay, if I've got 32 heads, for example, and I've got 8 GPUs, then I'm going to divide up the different heads by the number of GPUs that I have. Similarly for the key value heads. So again, you got to probably code these things so that the math works out with the hardware that you're using, but the idea still applies. You're going to divide up the number of key value heads by the model parallel size. And this matters because we're going to be essentially computing the attention scores in parallel, right? So one head is going to be addressing its corresponding keys. So one query head is going to be addressing its corresponding keys, and it's going to compute the attention scores for that particular query head. And that particular set of attention scores is completely independent of the attention scores of the other query heads. So hopefully that nails the point. The number of repetitions. So as I mentioned, in this visual, we're going to have to repeat this, right? We're going to have to repeat this exactly, according to the ratio of query heads to key value heads. So in this example, you would have to repeat these keys 2 times. And so that's what we're capturing here. And I think this was kind of like my reaction when I was going through it. Like I was just a little surprised that the head dimension carries sufficient information about the keys and values, because we're essentially kind of, we're doing away with this one-to-one correspondence here, and instead we're really compressing the information in the keys and the values. But nevertheless, the researchers show that it worked, and everything's empirically good. Surely somebody might even have come up with a proof that it works. So then we get into the actual implementation of the query, key, and value projection matrices. And this is where some of the parallelism comes into play. And I think this is following the Megatron pattern. I might be wrong about that, but take a look. And basically what you're going to see with this is you're going to split up the operations. You're going to split up the matrix, the weight matrix, by its columns. And it's useful to click in and just sort of see how this gets implemented. So the linear layer is defined as y equals xa plus b. A is parallelized along its second dimension. So essentially what this is doing is this is going to take some subset of the columns of A. And if you think about what happens when you do the matrix multiplication, let me see if I can try to do this. So you've got, x, which is, x, and it's going to have, elements. These are tokens. And then you've got matrix, the weight matrix, and it's going to have columns, right? And those columns are going to have to each get multiplied with, each of these rows. And so essentially what you can do is you can take, some chunk, like let's just say we take like half of this and these columns, and let's do all of the computations with, with these columns against all of the rows of this matrix. And then we'll do the same thing over here. We'll take these columns on a separate GPU, and we're gonna multiply them with the with your data matrix, and we can essentially compute the partial results of the output matrix. Neither portion of which relies on the other. You just need to squash them together in order to get the final result. That's what the column parallel layer is doing, and that's sort of the easy one. That one's easy to think about. Same deal with the key projection matrix. Same deal with the value projection matrix. The only interesting difference here is that, again, you are going to be projecting down to a much smaller vector space in the case of a smaller number of key value heads. So if you have 32 of these heads and you have 16 of these, well, you're going to have just like a way smaller vector space here than you will in the query space. And then next, the row parallel. So this is going to issue an all reduce at the completion of this layer, so that the model parallel workers will each have complete activation. So as I mentioned, you have sort of like a portion of the query, key, and value results on each of the GPUs. And again, I tried to nail the point that those are independent operations. But when you get to the output of the attention mechanism, all of that information gets recombined into a single vector, right? I said there are partial results on each GPU. That needs to come together now, and we're going to pass that through a final layer. And now we do this in a row parallel manner, and there's an all reduce that has to take place. So this one's a little harder to understand, but let's give it a go. So you've got, again, same approach. You've got y equals xa plus b. A is going to be split row-wise now, and X is going to have, it's going to be split by its columns, right? So its second dimension is going to be its columns. Now, I'm assuming two-dimensional matrices here too. There's probably some higher dimensional generalization of all of this. But if you think about what happens in that scenario, I'm gonna attempt to draw this because again I'm just riffing here. So you've got, again, the first matrix is your data matrix, and what did we say? We're going to split this by column. So we're going to take these, but you know, the thing to keep in mind is that originally this is laid out where each row corresponds to a token or a subtoken, and what we're going to do instead is actually split this up by columns. And then the weight matrix gets split up by rows, right? So that's the row parallel aspect of this. And essentially we're taking rows of this and we're splitting up the computations in that manner. So let's just consider this slice here, right? So this slice is going to get multiplied with, you know, call it this slice here. And if you think about the necessary computations that go into the output matrix, this cell requires a full dot product with this column and this row. And so you can see the issue, right? The issue is that we have a partial computation of this going into here, and then we're also going to have this getting done in parallel. And the point being is that this also needs to go here. So what we're doing is we're materializing, n copies of this matrix in parallel, and then what's going to happen is they're going to get all reduced so that each worker in this this parallel environment now has a complete copy of this matrix. You've got the cache for keys and values, and as I mentioned, during decoding this is important because when you get a new word that comes in at decoding time, again, we're generating tokens. We've got our input prompt, and we're going to generate words one word at a time, and we're going to have to query against the keys and values that are already, you know, present for previous words. So we're going to cache those results. It would never make any sense to feed in the entire input sequence at every decoding step. So really all we do is we take one word at a time, feed it into the model, and we're going to compute the attention scores and, you know, implement the attention mechanism against all of the keys and values that are already computed. And so we're going to store them in a cache. This is essentially just a tensor. This is a tensor inside of a module. And so, you know, I got to be honest, like there's like some details about PyTorch that I'm not really an expert on, but this is not treated as a parameter. This is a tensor, and so, you know, it's not like there's going to be like gradient computations performed on this or you know, computational graph tracking. I'm not sure why this is getting pushed to CUDA, but I think it might be because if you do like model to device, it's going to take the parameters and push them to the device, but this is a tensor, and so I think what might happen is this might get left behind on the CPU, and so maybe they're calling CUDA in advance of that. So then we're into the forward pass of the attention mechanism. This is going to be a long video. The attention mechanism is going to essentially take an input, which might be, you know, a prompt, it might be, you know, an incremental token that needs to attend to all previous tokens. And so what it's going to do, we're going to pass that, you know, that sequence of tokens through the query projection matrix, the key projection matrix, and the value projection matrix. And so now we have activations for that, and we're going to reshape. So you know, again, I'll point out some details that, like, I've like come to appreciate as I've spent more time with working with GPUs and just computer science in general. So this is a view, right? So we're taking the data which is laid out as batch size, the sequence length, and the dimension embedding, and it's laid out in that fashion in memory. So you've got for an entire element, an entire example from your batch laid out in memory first. Then you're going to go on to the second element in your batch, and within each of those chunks you're going to have the first token in your sequence. You're going to have and within that you're going to have dimension 1, dimension 2, and so on and so forth. And so what's happening here is, instead of considering the last dimension to be the dimension of the tokens, which in this example, in this model is 4096, what we're going to do is we're going to imagine that there's actually a break. So instead of 4096, we're actually going to break that into, I don't know, call it like 32 chunks. And so, the math works out that then you have, one portion of the token embedding, followed by another portion of the token embedding, and so on and so forth. The point being is that it doesn't change the layout in memory. And so I think it's interesting when you see something like view, like it's like a somewhat intentional choice. Whereas if you were to meaningfully change the layout of this data, maybe a transpose or something like that, you would actually have to move data in memory, and it's those kinds of things that are actually somewhat expensive when it comes to GPU operations. So just want to give a little nod to the fact that there's a lot of computation happening. Just being a little thoughtful about efficiency and what's happening on the GPU with respect to memory and computation. It's these kinds of details are worth thinking about. Now we're getting into the rotary embedding stuff, and so there are actually a lot of details with this. So if we go back up to the rotary embedding, the rotary embeddings are essentially taking pairs of dimensions in the word embedding, and they're rotating them, and they're rotating them according to two things. First, where you are in those 4096 dimensions. So you could be at the 0th index and the first index, and that would be a pair of elements, even and odd element, even and odd with respect to the indices. And that's going to influence the amount by which we rotate those two dimensions. And similarly, if it's token, if it's a token at sequence index 0, or if it's a token at sequence index 10, that also influences how much the pair of dimensions are going to get rotated. Basically, what the frequencies are doing is it's telling you what that rotation ought to be, and you can see there's some skipping, by twos, right? And that's the pairing that I'm talking about. Is every 2 dimensions there's going to be some change, and then there's also this other factor that I was describing. There's the so the end. So if we actually go and look, I think end is going to be the max sequence length that can be generated, which for this model is 2048. So let's see if we can pre-compute frequencies. So this is, again, the max sequence length, and they do ×2, and right now we're in the main transformer block. I think this is the init method of the transformer. I think this might account for the even and odd dimensions, or it might give us some extra capacity. I haven't thought really hard about it, but nevertheless, so for all intents and purposes, think of t as the as the sequence length 0 all the way up to 2047, and we're going to take the outer product of that. You know what? Let's actually just check what happens down here. Let's run a little bit of code. Let's focus in on a word embedding size of 4096. Let's say there would be a sequence length of 10, for example, and data is 10,000 according to the rotary paper. So we're going to pre-compute this frequency set. So let's take a look at what gets returned from this. All right, so here we are in the code, and I'm just kind of following along with what they do in the transformer block. So you take the dimension, which is 4096, you divide by the number of heads, which is 32, and so what does this wind up being, like 128 or something? Yeah, that's 128. And so what we're going to do is, and then end is 10. So let's just assume like the maximum sequence length is 10. So this is essentially feeding in 128 and 10 and 10,000 into this. So now we're inside the function, and let's just kind of step over and take a look at what these objects are like. So again, we said the dimension for the input was 128. So yes, so we're going to take half of that. And we're going to establish frequencies for half of that, and that again corresponds to that coupling, that pairing that I was talking about. So every pair of your token embeddings is going to be treated in a particular manner. I told you that that pair location, the index of that pair, in addition to the position of the token in the sequence, are going to influence how much those pair of points get rotated. And I guess like the right way to think about those pair of points is that they're inducing a vector in 2 dimensions in R2. And so now if we look at what happens in if we look at the outer product, so again T is a length 10 vector, and I'd say just know that it's like it's incrementing the sequence length. And you look at freaks now, it's going to be the outer product of those two. So you're going to see basically the product of 0 and whatever was in freaks along all 64 elements. And so that's why we're seeing 0, 1, 2, 3, 4, 5 up to 9. And then we're seeing whatever was in frequency at position 0, blah blah blah, blah. And so it's that's the outer product. And I guess probably the only interesting thing to note at this point is that you can basically think of this operation as a operation over complex numbers. There's an isomorphism between R2 and a complex number, and in particular, in this case, we're treating this as a like a little 2x2 orthogonal matrix, where you're not scaling your magnitude of your input vector at all. You're simply rotating it by the frequency amount, and that's kind of your theta by which you're rotating, right? So that complex numbers are made up of a real and an imaginary component, and the imaginary component is sort of what gives you the rotational aspect. And so what's happening here is we're instead of thinking about a block diagonal matrix where you could have a little 2x2 matrices along the diagonal, sines and cosines, that would be orthogonal matrices along the diagonal. Rather, what we can do is we can think of this as I think you would think of it as a matrix of complex numbers with essentially half as many rows, half as many columns, and that way when you do the multiplication, what happens is you're multiplying each of your input vector elements with the complex number along the diagonal, and the math works out such that this corresponds to exactly the kind of rotation that we're looking for. So just wanted to give a little maybe overly detailed explanation of sort of what's going on with the complex numbers. And I think if this isn't clear, there's obviously a ton of resources on YouTube, and for me it was Linear Algebra Done Right by Sheldon Axler that was really helpful for understanding this isomorphism that I was talking about. We're essentially going to apply those rotary embeddings to the queries and keys, and I should have said that this is so that we know we have positional information. So if you think about the self-attention mechanism, it is invariant to different permutations of the input sequence. So you could attend to an earlier position or the current position or one position away, and you would have no way of knowing if a particular token came before the current position or after the current position, is close to the current position, and so on and so forth. So what this is doing is this is giving the model a notion of how far away a particular token is. And essentially, I think people kind of hypothesize that the model just memorizes the modification that takes place here. So we know, so it knows that like this little rotation corresponds to an element that's, a certain distance away. It's sort of unclear if it's actually internalized that property of, okay, rotating by a certain amount corresponds to looking, 5 steps back, so on and so forth. I think digging into those details could be interesting. I'm not exactly sure why they're moving the cache to the same device as the query. I mean, obviously, to perform the computation that way, you're going to need that. But maybe this is due to the fact that we're in the model parallel environment. And then we go on to updating the cache. So start position, we're going to come to that when we talk about decoding, and then we look at so the sequence length is going to be pretty long for an input prompt, but when you get to decoding, the sequence length is really just 1. So what's happening here is we're updating our cache so we can come back to it later when we're decoding. So we're taking the current keys and values that we generated, and for all of the elements in our batch size, we're going to go from the start position to the start position plus the sequence length. Again, we define the sequence length based on what was in the batch, and we're gonna set the elements of that cache, which was initialized to be a bunch of zeros. We're gonna fill that in now, so that way we have that to come back to when we're decoding. And next we are, I guess, just pulling everything up to the current position, so all of the keys up to the current position. So in this case it was just incremental. In this case we're taking everything up to the current position. Same thing for the values. This is the repeating that I was talking about. Let me take a quick look. What's happening is that we're repeating the keys and values, and again, this is because of the grouped query attention, where you're taking, you're leaving the, the batch size, the sequence length, the number of attention heads. You're giving yourself an extra dimension here. You're expanding. So you're expanding, right? So this is going to be the number of repetitions. And then you're going to reshape and get those back together. So you've got batch size, the sequence length, which might be like 2048. You've got the number of key value heads times the number of repetitions that need to be replicated in order to have that one-to-one correspondence between your query heads and your key value heads. And so that's what that's doing. That's the repeating. So you do that for your keys and your values. You then need to do some reshaping in order for all of the attention calculations to work out. So you take your query matrix and you transpose it so that it's got the following shape. You've got a batch size, the number of local heads. Again, model parallel, so we're just focused on the attention computation that needs to take place on the current GPU. The sequence length, and you have the head dimension. So that's the layout here, where the big difference is that we've swapped these two dimensions. So before it was sequence length and local heads, now it's reversed. Same deal for the keys and the values. I introduced this variable just so I could sort of keep track of things. So one more swap takes place on the keys. So you're swapping 2 and 3. So these two get swapped. You can see sequence length head dim here, and then this is head dim sequence length. And so what's going to happen is when you take the matrix multiplication between the queries and the keys temp, as I've called it, You've got batch size, n local heads, and then you've got, you know, head dimension matching the column space, or sorry, the row space, right? So this would be the you know, the column space of this matrix is matching the row space of the queries. And so what you're going to wind up with is, you know, the head dimension getting collapsed, right? We're taking a dot product according to the token head dimension, and we're going to be left with a sequence length by sequence length matrix, right? Which makes sense because we're talking about attending to all positions in the sequence, right? That's the self-attention mechanism. And so then you just do a little division by the square root. I think the reasoning for this, which I probably need to review the details of, is just that you essentially will blow up. You know, the dot product has the potential to grow in magnitude, and so this might be a way of keeping your activation values in a reasonable range. So then, you know, this mask is used to prevent the model from attending to future positions. So if I'm at sequence position 10, I cannot attend to position 11 and beyond. I can only attend to position 0 through 10. And so what this is going to do is it's going to add a ginormous negative infinity value, which when passed through the exponential function for the softmax is going to give you a really tiny value, right? And so if we induce a probability distribution over activation scores, which is what's happening here, then you know, a large negative infinity value is basically going to contribute to, you know, it's going to be a zero probability. So essentially a particular position that can't attend to a future position, it's basically going to have zero probability weight on looking at the values of that future position. And so so that's how we get our weights. We then combine the scores with the values so that we can actually get that weighted average of the values, which is, you know, information about the tokens. And this is you know, almost our output. We still have to mash all of that information together. Again, remember, we're in parallel, so we have partial. You know, we have you know, part of the output. We have some of the you know, attention computations, you know, for a portion of the heads on this particular model parallel device, but there are other model parallel devices that have other information, and the output matrix is aware of that, and it's going to essentially, you know, use that, you know, take the information from the different devices. It's going to do the row parallel computation, do that all reduced, so that way when we return from this attention mechanism, we have all of the activations necessary to move on to the feed forward layer. So now we're going to move on to the feed forward layer, which is the next block in the attention architecture. So there's some funky stuff going on with the attention block, or sorry, with the feed forward block. So you take your dimension, right? So let's just look at the arguments. You know, got dimension, which might be something like 4096. You've got the hidden dimension, which is going to be something larger. In general, I think what happens with the feed forward network is it's two layer. It tends to be two layers. One blows out the dimension in a really huge manner. You know, I don't want to speculate too much about like sort of what's happening there, but you know, maybe one possibility is that it's sort of like a pattern recognizer, and it's you know, looking for a huge number of patterns, and by, you know, passing it through that really massive vector space, you're able to select out some of those patterns. You know, syntactic patterns, you know, genders, you know, semantic relationships, subject, object, predicate type relationships, so on and so forth. And so then there's this multiple of, Yeah, so this multiple of, again, I don't know if this is a like hardware optimization. It comes in down here. Not entirely clear. I haven't read the paper, so I probably ought to read the paper. Then there's this feed forward network dimension multiplier. But let's look at this, because this is kind of weird. They take the hidden dimension, which might be some large quantity. Like, let's see if the hidden dimension is defined anywhere for like the 70 billion. Like, let's go down into the transformer itself. So when you initialize, okay, so it's probably going to be in the transformer block. When you initialize the transformer block, like, what happens in the feed forward? Okay, so you've got hidden dimension, which is 4x, right? So there's that proof that I was saying that it's going to be larger. So you've got the hidden dimension, which is like 4x, so 4096 times 4, and then you've got multiple of, and so for some sensible defaults, so multiple of is 2056, multiple of 4096. This is probably for like nice divisibility. Maybe it's a hardware optimization. And then the FFN dim multiplier, I think it's none in the case of the 7 billion model. It's 1.3, which is a greater than 1 in the 70 billion case. And so let's see if we can like reason about what is going on here. So this is multiplying by 2/3. So the hidden dimension we said was 4 times 4096. We're going to take 2/3 of that. Why? I have no idea. And then we are going to take that hidden dimension and multiply it by a multiplier, which it defaults to 1, so there's no multiplier. But in the case of the 70 billion model, we're getting an upscale. We're scaling up in that manner. And then the final hidden dimension, this is, again, that like blown out hidden dimension is going to be hidden dimension plus multiple of, which would be like 256 or something like that, minus 1. So that's like 255 plus hidden dimension. So we're like dividing by multiple of. So it's like kind of like, what's my hidden dimension? Like, how many 256 chunks can I fit into that? And then, take those number of chunks, multiply it by 256, and that gives me my hidden dimension. Probably need to read the paper to understand why these decisions were made. Presumably there's like a principled reason why. So, this is the usual business, and I think this is where maybe the video might go a little bit faster, because we know what's happening with a column parallel linear layer, right? We're back to the model parallel scenario, where we're taking columns of our weight matrix and multiplying it with all rows of our data matrix. And so we're going to do that operation in parallel and take advantage of the multiple GPUs. Now, W2, this is like a slightly funky feed forward network. This is not the standard transformer architecture. They're doing sort of like this gated thing, and I need to take a closer look at this paper. Maybe people have seen this before, but there's like some gated mechanism that basically, it's sort of like this, like, it's basically like a ReLU, but it doesn't have this like dead zone. So if you're like just below 0, you're still like the neuron's still alive. I think the issue with ReLU is that when things dip below 0, when activation values dip below 0, your neuron dies. And I don't know how often it recovers from that. So this may be a way, for the neuron to recover a little bit. It gives you a little bit of smoothness here. And so what's going to happen is we are going to pass our data through, there's 3 layers here. We're going to pass our data through layer 1, and we're going to pass it through that activation. So some of the data is going to pass through. Some of that data is going to get clamped to 0, essentially. We're going to also pass that data through another matrix. We're going to do an element-wise operation. So you can imagine some of the entries of this element-wise multiplication are going to be basically 0, and some of them are going to be larger than 0, right? So that's essentially the outcome of this. You've got some 0, some positive, and again, we're going to then take the result of that and pass it through a second linear layer. So this, W1 and W3 are the, the big dimensional vector spaces. You can see that's like, blowing out 496 to, 4x that, or whatever the multiple is. And then this W2 is projecting you back down to the embedding size. So that's the feed forward. I need to do a little more digging on that. So if anyone has any links to explanations for this, I probably just need to take a closer look. So now we're just going to assemble what we already have, right? So we said that a transformer is made up of blocks of this repeated pattern of attention followed by a feed forward neural network. So we're going to assemble those pieces here. So this is a block. So one block is going to get repeated, 32 times or 100 times or, a bajillion times if you're OpenAI. And so you've got the attention block here, the feed forward block, and you're, parameterizing that with whatever values you need. We talked about that above. The only thing we didn't talk about is RMS norm. So this is essentially layer norm, but computed in a more compute efficient manner. So let's just take a quick look at what RMS norm does. So this is based on this paper from 2019 that basically goes through the details of the original layer norm, which is going to take each of your feature embedding dimensions, subtract off the mean, divide by the standard deviation of all of those different embedding parameters. Sorry, those embedding features. And I don't know if the G term is all that common, but nevertheless, you're taking that and then you also you pass it through another function that allows the model to undo that scaling. And people probably know what layer norm is doing. It's an attempt to overcome internal covariate shift. This is this idea that your weights are shifting around during training, and so in order to keep your activations in a range that makes sense to all of the layers as they're moving around, you're sort of trying to scale them so that they kind of follow maybe a normal distribution or something like that. That way you sort of remove out some of the noise associated with back propagation and training. And so the simplification here is that we are, instead of subtracting off the mu term, instead of subtracting off the average of those feature dimensions, we're going to not subtract off the mu, and we're simply going to divide by I guess maybe a biased root mean squared error, or root mean square of the feature dimensions. So you're computing that mu essentially, minus the square term, taking the square root, and nevertheless, the hypothesis of this paper is that that's all you need, and that empirically works just as well, but that you save a little bit of computation, and who knows, maybe it works better. But that was the decision that was made, and so that's the RMS norm. Now, I think another change that was made, and forgive me if I'm late to the party, but another change that was made to a lot of the transformer architectures from the original one, maybe they would have performed it after the attention mechanism, because in this case you can see it's being applied before the attention mechanism, and then similarly there's another norm that gets applied before the feed forward layer. So I think the traditional transformer architecture uses post norm, where normalization occurs after the layer. But I think people found that these models are just more stable to train if you do a pre-norm. Okay, and so we are really cruising here. We're pretty much done. You've got now the transformer layer, which you just assemble everything together. I thought this was interesting that the parallel embedding splits column-wise. I don't know why, my first reaction to what this ought to be was that maybe you would split by rows, like, a portion of your vocabulary would live on a different server. Um, but yeah, that like it's not immediately obvious how you would go out and issue a request for token embeddings. You get like a sequence, and you need certain tokens associated with that sequence. You send that request out to each of the servers, and like it's only going to fulfill part of that, and then you need to know like sort of how they get you know sequenced appropriately when all of them come back together from the different model parallel workers. So a better idea, which I think, is to take your embedding matrix and split it vertically. So you take the first k dimensions of your word embedding matrix, you send it to a model parallel worker. You take the next k dimensions and send it to the next model parallel worker, and so on and so forth. And then when you issue the request for a set of tokens, you're going to split that workload across all the model parallel workers, and all you have to do is do a row-wise concatenation. So again, it's instructive to like go in and see how this happens. And I think what was really cool for me with seeing this is that like you can actually get into the details of how the GPUs are communicating with one another. So you just kind of keep drilling in until you see a reduction. So you see like, okay, gather from model parallel region, gather, just keep going until you get to this, and now you're finally at a stage where you see the all gather. And like it's just nice to like be able to drill into that. Surely we could do the same with something like FSDP, but it's nice when your like intuitive understanding matches up with sort of the code. And if you look at this is again, they're concatenating along the last dimension, and I just thought that was interesting, so I just wanted to share that. And so that's so that's like the first piece of a transformer. You got to look up the embedding for the input. Now we're gonna go through all of the transformer blocks, something like 32 of them. You do one final normalization. Again, we were doing pre-norm, not post-norm, so we're going to do one final normalization, and then you're going to do an output. So you're going to take the activations of the final layer, and you're going to pass it through a final linear layer, which is going to compare the activation with it's basically going to select out the next word is really what it's going to try to do. If you're decoding, if you're trying to predict the next word, it's going to give you a score, a distribution, logit scores over your vocabulary, and it'll, if you select the most probable one, that would be like greedy decoding, and that's the next word. Or you might do some sampling over that distribution of next words. This is where the rotary embeddings comes into play. So we're going to define the rotation matrix that we talked about here, and we're going to pre-compute that. There's no sense in doing that for say every forward pass. Now the forward pass, you look up your token embeddings, you move the rotation matrix onto the device that you're working on. The mask, if it's provided, is going to be filled with the negative infinity values that I was talking about. You're going to want to basically, so you've got this like matrix that's filled with negative infinity. It's broadcastable. You've got like one in the position of the batch dimension and the sequence, one in the position of the what I would imagine is the number of attention heads, and then you've got sequence length by sequence length, so this is going to get masked onto the attention mechanism. And so what we're going to do is I think we're going to zero out, upper triangular mask is going to basically zero out all of the like lower elements, lower left elements of the matrix. I just need to like think a little bit more about why this is the right thing to do as you decode further. If you consider the rows to be your queries, then you shouldn't be able to query. Like, it's clear that on, like, the starting position, when starting position 0, basically this is going to correspond to, an element 0 along the diagonal and below, and you're going to have negative infinity in the upper right portion of this matrix. And basically that means that, like, position 0 in your sequence can attend to itself, but it can't attend to anything beyond that. Position 2 can attend to, index 0 and itself, but nothing beyond that. I need to think through, like, why moving that, the things that can be attended to up further makes sense as you decode further. But yeah. So then, you apply all of your transformer blocks, apply the final RMS norm that we talked about. Output, kind of interesting, they like cast to float. I didn't call that out. But yeah, there are like a bunch of places where they cast to float, so you can assume that, like, most of these computations are taking place in brain float 16 format or FP16 format. But in a couple places, they do upcast to floating point numbers, presumably for stability. I have to imagine that when you upcast to, for the output here, that's useful for, like, a loss calculation where you might need a lot of precision. Same thing for, like, the softmax. So I think that about does it for this video. Probably going to go through like another video showing the generation script. So I think it's worth going through the generation script. I think, this is another one of those situations where everybody just uses Hugging Face's generation facilities, which is amazing, right? It's like one of those, like, amazing things that is just, like, works right out of the box. But you don't, fully get the details of what's happening when you use a parameter like top P, or, temperature dampening of your sampling distribution. So I think it's worth seeing those things at least once. And then the other thing that was really cool about this is sort of like demystifying what's going on behind the scenes, and what the special characters are when you interact with the model in a chat scenario. I've always wondered sort of like what OpenAI was doing, and I think this makes it pretty clear. So I think I'm going to cut it here. Hope you enjoyed this. Sorry, this was like pretty impromptu and off the cuff. If you have any questions, paste them in the chat. If you have any resources, I am all ears. Thanks.